Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The history of science reveals a relentless pursuit of understanding, a drive to illuminate the hidden mechanisms governing our world. Among the figures who stand as beacons in this quest for knowledge, Abu Ali Alhazen Ibn al-Haytham, known in the West as Alhazen, occupies a position of particular significance. His meticulous approach to optics, coupled with a profound skepticism of established dogma, marks a pivotal moment in the development of the scientific method. Alhazen's impact resonates even today, shaping our understanding of light, vision, and the very process of scientific inquiry. Alhazen's most influential work, Kitab al-Manazir *, Book of Optics *, emerged from a dissatisfaction with existing theories of vision, particularly those presented in Ptolemy's *Optics *. Ptolemy, a towering figure of antiquity, proposed that vision occurred through rays emanating from the eye, actively probing the external world. This extramission theory, as it was known, had held sway for centuries. Alhazen, however, found this explanation fundamentally flawed. He questioned how the eye could perceive objects at great distances instantaneously, and how it could differentiate between the light emanating from different objects in a complex scene. These inconsistencies prompted a radical re-evaluation of the visual process. To address these shortcomings, Alhazen embarked on a program of systematic experimentation, a hallmark of the scientific approach. He recognized the limitations of purely theoretical speculation and emphasized the need for empirical evidence to validate or refute hypotheses. This emphasis on observation and experimentation represented a departure from the prevailing philosophical traditions of his time, which often relied on deductive reasoning and appeals to authority. Alhazen championed a methodology where observation served as the foundation for building knowledge. One of Alhazen's most ingenious contributions was his development and utilization of the camera obscura. This device, essentially a darkened room with a small hole in one wall, projects an inverted image of the outside world onto the opposite wall. Alhazen meticulously described the phenomenon, noting the sharpness and clarity of the projected image, as well as its dependence on the size and shape of the aperture. He understood that light travels in straight lines and that the pinhole acts as a selector, allowing only a narrow beam of light from each point in the visual field to enter the camera. These beams then intersect and form an inverted image. Alhazen's experiments with the camera obscura provided compelling evidence against the extramission theory of vision. The fact that an image could be formed without any active emission from the eye suggested that vision was a passive process, involving the reception of light rather than its projection. He argued that light rays originate from objects and travel to the eye, where they are processed to create a visual representation of the external world. This intromission theory, as it became known, formed the cornerstone of Alhazen's new model of vision. In Book of Optics Alhazen documented a series of experiments on light refraction and reflection. He meticulously measured the angles of incidence and refraction for light passing through different media, such as air and water. He observed that light bends as it passes from one medium to another, and that the amount of bending depends on the properties of the two media. These observations led him to formulate a preliminary understanding of the laws of refraction, although he did not arrive at the precise mathematical formulation later developed by Snell. Alhazen also conducted extensive experiments on reflection, studying the behavior of light when it strikes mirrors of various shapes. He demonstrated that the angle of incidence is equal to the angle of reflection, a fundamental law of optics. He further investigated the formation of images by curved mirrors, analyzing the effects of concave and convex surfaces on the magnification and distortion of reflected images. His geometrical analysis of reflection laid the groundwork for later developments in optical instrument design. Alhazen's influence extended far beyond the realm of optics. His emphasis on empirical observation and experimental verification had a profound impact on the development of the scientific method. He demonstrated the power of combining theoretical reasoning with careful observation, a principle that became central to the scientific revolution. His work served as a model for future generations of scientists, inspiring them to question established dogma and to seek answers through systematic experimentation. Roger Bacon, the 13th century English philosopher and scientist, was deeply influenced by Alhazen's Book of Optics *. Bacon, himself a strong advocate for the experimental method, recognized the importance of Alhazen's work and promoted its dissemination in Europe. He translated portions of Book of Optics * into Latin and incorporated Alhazen's ideas into his own writings on optics and natural philosophy. Bacon's advocacy helped to ensure that Alhazen's contributions were recognized and appreciated by European scholars. Johannes Kepler, the 17th century German astronomer, also drew inspiration from Alhazen's work. Kepler, famous for his laws of planetary motion, applied Alhazen's geometrical approach to optics to understand the functioning of the eye. He used Alhazen's ideas about refraction and image formation to explain how the lens of the eye focuses light onto the retina, creating a clear image of the external world. Kepler's understanding of the eye as an optical instrument was directly influenced by Alhazen's pioneering research. Alhazen's legacy endures in our modern understanding of optics and the scientific method. His emphasis on empirical observation laid the foundation for the development of modern experimental science. His meticulous documentation of experiments, his careful analysis of data, and his willingness to challenge established theories all exemplify the principles of scientific inquiry. The camera obscura, which Alhazen so skillfully employed, remains a valuable tool for teaching and demonstrating the principles of optics. The problems Alhazen tackled, such as the true mechanism of sight and the behavior of light, remain at the heart of optical science. His solutions, while refined and expanded upon over centuries, still resonate in the fundamental principles taught today. His influence extends to the design of modern optical instruments, from telescopes and microscopes to cameras and lasers. The enduring relevance of Alhazen's work underscores his position as a true pioneer of scientific thought. His legacy resides not merely in specific discoveries, but in the paradigm shift he initiated, a shift towards empirical validation and a relentless pursuit of understanding grounded in observation. Alhazen's commitment to empirical validation and meticulous observation extended profoundly into the realm of geometrical optics. He confronted a significant deficiency in the prevailing an understanding of light's behavior, a lack of precise mathematical models to describe its interactions with various media. Existing theories, largely derived from the works of Euclid and Ptolemy, offered qualitative descriptions, yet fell short of providing a quantitative framework for predicting and explaining optical phenomena. Alhazen sought to rectify this by developing sophisticated geometrical techniques that allowed for a rigorous analysis of light's reflection and refraction. His approach involved a deep engagement with the principles of Euclidean geometry, which he skillfully adapted to the study of optical phenomena. He employed conic sections, such as parabolas, ellipses, and hyperbolas, as tools to model the curves formed by reflected and refracted light rays. This innovative application of geometrical constructs provided a means to represent and analyze the behavior of light with unprecedented precision. The cornerstone of Alhazen's work in geometrical optics lies in his formulation of the law of reflection. While the basic principle that the angle of incidence equals the angle of reflection was known previously, Alhazen provided a comprehensive and mathematically rigorous demonstration of this law. He meticulously analyzed the reflection of light from various surfaces, including plane, spherical, cylindrical, and conical mirrors. His analysis extended to both convex and concave mirrors, meticulously mapping the paths of incident and reflected rays. He demonstrated that the law of reflection holds true regardless of the shape or orientation of the reflecting surface. Alhazen's detailed geometrical analysis of reflection in mirrors, as documented in his monumental work, Kitab al-Manazir, represents a significant advancement in the field of optics. He presented a systematic and exhaustive treatment of the subject, providing detailed diagrams and geometrical proofs to support his claims. His work served as a comprehensive guide for understanding the behavior of light in reflecting systems, influencing subsequent generations of optical scientists. In addition to his work on reflection, Alhazen made substantial contributions to the understanding of refraction, the bending of light as it passes from one medium to another. He recognized that light changes direction when it enters a different medium, such as from air into water or glass. He embarked on a systematic investigation of this phenomenon, seeking to uncover the underlying mathematical principles that govern its behavior. Alhazen's approach to studying refraction involved a combination of experimentation and geometrical analysis. He carefully measured the angles of incidence and refraction for light rays passing through various transparent materials. He then attempted to develop a mathematical relationship between these angles, aiming to formulate a law of refraction analogous to the law of reflection. While Alhazen did not arrive at the precise formulation of Snell's law, which mathematically relates the angles of incidence and refraction to the refractive indices of the two media, his work laid important groundwork for its eventual discovery. He recognized that the amount of bending depends on the properties of both media involved. He also observed that the angle of refraction is always less than the angle of incidence when light passes from a less dense to a denser medium, and vice versa. Alhazen's geometrical analysis of refraction in lenses represents another significant contribution to optics. He meticulously studied the behavior of light as it passes through lenses of various shapes, including convex and concave lenses. He demonstrated how lenses can be used to focus light rays, forming images of objects. His work provided a foundation for understanding the principles underlying the operation of optical instruments such as telescopes and microscopes. In Kitab al-Manazir, Alhazen presented detailed diagrams and geometrical constructions to illustrate the behavior of light in refracting systems. He analyzed the formation of images by lenses, determining the locations and sizes of the images formed. He also investigated the effects of lens aberrations, imperfections in the image caused by the non-ideal behavior of light rays. Alhazen's work on refraction had a profound impact on the development of optics. His meticulous experiments and geometrical analyses provided valuable insights into the behavior of light as it passes through different media. His investigations paved the way for later scientists, such as Willibald Snellius and René Descartes, to discover the precise mathematical law governing refraction. The geometrical methods developed by Alhazen continue to resonate in modern optical design and ray tracing. His approach to analyzing the behavior of light using geometrical constructs remains a fundamental principle in the design of lenses, mirrors, and other optical components. Modern optical design software relies heavily on ray tracing techniques, which are based on the same geometrical principles that Alhazen pioneered centuries ago. Euclid's geometry provided the essential foundation upon which Alhazen built his optical theories. The rigor and precision of Euclidean methods served as a model for Alhazen's own approach to scientific inquiry. Ptolemy's optics, with its detailed observations and geometrical analyses of optical phenomena, served as a direct inspiration for Alhazen's work. Alhazen expanded upon Ptolemy's ideas, correcting some of his errors and providing more comprehensive explanations of optical phenomena. Johannes Kepler, whose laws of planetary motion revolutionized astronomy, was demonstrably influenced by Alhazen's geometrical approach to optics. Kepler's use of geometrical methods to analyze astronomical observations reflects the influence of Alhazen's emphasis on mathematical precision and geometrical rigor. The application of conic sections, a technique central to Alhazen's optical analyses, also appears prominently in Kepler's work on planetary orbits. He, too, employed such methods to model the elliptical paths of planets around the sun. Alhazen's systematic investigation of reflection and refraction, his meticulous experiments, and his rigorous geometrical analyses established a new standard for scientific inquiry in the field of optics. His work represents a pivotal moment in the history of science, marking a transition from qualitative observation to quantitative analysis and mathematical modeling. His legacy resides in the enduring influence of his ideas on subsequent generations of scientists and engineers. The modern relevance of his geometrical methods underscores his position as a true pioneer of optical science. His contributions were not merely historical curiosities, but rather foundational elements upon which modern optical technology is built. Alhazen broadened his optical investigations to encompass the Earth's atmosphere. He sought to explain phenomena such as twilight, dawn, and the sky's characteristic blue hue, all of which stem from the interaction of sunlight with the atmosphere. Contemporary understanding of these effects remained rudimentary, lacking a cohesive theoretical framework. Alhazen addressed this deficiency through a combination of observational analysis and geometrical reasoning, developing a model of atmospheric refraction that accounted for these visual phenomena. Twilight and dawn, the periods of gradual transition between day and night presented a particularly intriguing challenge. Earlier explanations often relied on vague notions of light scattering or reflection from distant objects. Alhazen, however, proposed that these effects arose from the refraction of sunlight as it passed through the Earth's atmosphere. He reasoned that even when the sun was below the horizon, its rays could still reach the observer through atmospheric refraction, bending the light path and illuminating the sky. To support his theory, Alhazen meticulously analyzed the geometry of the Earth and its atmosphere. He considered the atmosphere as a series of concentric layers, each with a slightly different refractive index. Sunlight entering the atmosphere at an oblique angle would be progressively bent as it passed through these layers, resulting in a curved path. By calculating the amount of refraction at different altitudes, Alhazen demonstrated how sunlight could reach the observer even when the sun was below the horizon, thus explaining the phenomenon of twilight. His analysis extended to the duration of twilight, which he correctly attributed to the height of the atmosphere. A taller atmosphere would result in a longer twilight period, as sunlight would have to travel through a greater distance of air to reach the observer. Alhazen's quantitative approach, based on geometrical optics and atmospheric modeling, represented a significant advancement over previous qualitative explanations. A tangible example of Alhazen's work is his detailed analysis of the apparent change in the sun's position due to atmospheric refraction. He observed that the sun appears higher in the sky than it actually is, especially near the horizon. This effect, known as atmospheric refraction, is caused by the bending of light as it passes through the atmosphere. Alhazen accurately explained this phenomenon by considering the varying density of the atmosphere and its effect on the speed of light. Ptolemy's optics served as a direct influence on Alhazen's approach to atmospheric phenomena. Ptolemy had also discussed atmospheric refraction, but his treatment was less rigorous and quantitative than Alhazen's. Alhazen built upon Ptolemy's work, refining his geometrical models and providing more accurate explanations of atmospheric effects. Aristotle's meteorology with its observations of atmospheric phenomena, also likely contributed to Alhazen's interest in the subject, though Alhazen departed from Aristotle's more speculative approach by grounding his explanations in empirical observation and mathematical analysis. Alhazen's investigation into atmospheric optics also led him to propose a theory for the blue color of the sky. While he did not fully understand the underlying physics of light scattering, his explanation anticipated aspects of modern atmospheric science. He suggested that the air itself possessed a certain degree of opacity, causing it to scatter sunlight in different directions. He further proposed that blue light was scattered more effectively than other colors, resulting in the sky's characteristic blue appearance. Modern science has since refined this explanation, attributing the blue color of the sky to Rayleigh scattering, a phenomenon in which light is scattered by particles much smaller than its wavelength. Rayleigh scattering is most effective at shorter wavelengths, which correspond to blue light. Alhazen's insight that the air itself plays a role in scattering sunlight, with a preferential scattering of blue light, was a remarkable intuition given the limited scientific knowledge of his time. The modern relevance of Alhazen's work on atmospheric optics is evident in its connection to modern atmospheric science. His models of atmospheric refraction and his explanations of twilight and dawn laid the groundwork for later investigations into these phenomena. Scientists continue to study atmospheric optics, using sophisticated instruments and computer simulations to model the behavior of light in the atmosphere. Alhazen's pioneering work serves as a reminder of the importance of observation, experimentation, and mathematical modeling in understanding the natural world. Later scientists who studied atmospheric optics and scattering were directly influenced by Alhazen's work. While pinpointing specific individuals who explicitly cited Alhazen's atmospheric studies proves challenging due to the historical context and limited access to sources, his general optical theories, disseminated through translations of Kitab al-Manazir undoubtedly shaped the discourse on light and vision, indirectly influencing later investigations of atmospheric phenomena. Scholars examining twilight, refraction, and sky color, even if unaware of Alhazen's specific atmospheric arguments, benefited from the broader scientific framework he established for optical inquiry. His emphasis on empirical observation and mathematical analysis provided a methodological template for future researchers in the field. Alhazen's detailed analysis of twilight phenomena, his explanations of the sun's apparent size near the horizon, and his proposed theory for the blue color of the sky represent a significant contribution to the field of optics. His work not only advanced the understanding of atmospheric phenomena, but also demonstrated the power of scientific inquiry in unraveling the mysteries of the natural world. His legacy resides in his enduring influence on subsequent generations of scientists and his role in shaping the scientific method. The methodological rigor that illuminated the study of atmospheric phenomena found parallel expression in his exploration of pure mathematics and other physical sciences. The very same intellectual toolkit, a synthesis of empirical testing, geometric modeling, and a domain for logical proof, was a universal instrument in his hands. He applied it to problems ranging from the behavior of light in a darkened room to the foundational axioms of geometry and the esoteric properties of numbers. This versatility reveals a mind captivated by the underlying structure of reality, whether manifest in a ray of light or an abstract numerical relationship. One of the most elegant applications of his optical principles appears in his analysis of the camera obscura, or as he knew it, the albeit LMU-1E93LIM*, the dark room. The phenomenon itself was known, a small aperture in a dark space projects an inverted image of the sunlit world outside. For many, this was a curiosity, a pleasing natural magic. For Alhazen, it was an experiment demanding explanation. He moved beyond simple observation to systematically investigate the properties of the projected image. He correctly deduced that the phenomenon was a direct consequence of the rectilinear propagation of light. Each point on an illuminated object radiates light in all directions, but only the rays that can pass unimpeded through the tiny aperture continue in a straight line to strike the screen on the opposite wall. The inversion of the image was a simple, necessary outcome of this geometry. A ray from the top of an object passes through the hole and lands at the bottom of the screen, while a ray from the bottom lands on the top. His profound insight was to recognize the camera obscura as a physical demonstration of his theory of vision. If light travels from the object to the screen, It confirmed his intromission theory that light travels from the object to the eye. The aperture in the dark room functioned as an analog for the pupil of the eye and the screen for the retina. This connection was revolutionary. It transformed a parlor trick into a powerful pedagogical tool and an instrument of scientific verification. His work on the camera obscura laid the conceptual groundwork for its later adoption by Renaissance artists like Leonardo da Vinci and Johannes Vermeer, who used it to achieve unprecedented realism in perspective and lighting. The path from Alhazen's dark room in Cairo to Vermeer's light-filled studio in Delft is a long one, yet it is paved with the principle of light traveling in straight, predictable lines. This same insistence on geometric certainty propelled Alhazen into one of the most formidable mathematical challenges of his era, the problem of Euclid's fifth postulate, the famous parallel postulate. For centuries, mathematicians had been troubled by this axiom. While Euclid's first four postulates seemed self-evidently true, one can draw a straight line between any 2 points. For example, the fifth felt different. It read more like a theorem that ought to be provable from the other four. It states that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side. The complexity of its phrasing alone set it apart. Alhazen joined a long and distinguished line of thinkers, including Ptolemy and his contemporary Thabit ibn Qurra, who attempted to derive the postulate as a theorem. His approach, detailed in his asterisk commentary on the premises of Euclid's Elements asterisk, was exceptionally clever and influential. He proposed to replace the postulate with a different, seemingly more intuitive axiom that the locus of a point moving so as to remain equidistant from a straight line is itself a straight line. From this, he constructed a figure now known as a lambda quadrilateral, a four-sided figure with three right angles. He then attempted to prove that the fourth angle must also be a right angle, which, if successful, would have proven Euclid's postulate. While his proof contained a subtle flaw, it relied on an assumption that was itself equivalent to the parallel postulate. His methodology was groundbreaking. He was among the first to systematically explore the consequences of denying or altering Euclid's axiom, venturing into the conceptual space of what we would today call non-Euclidean geometry. His work was studied and built upon by subsequent generations of Islamic mathematicians, most notably Omar Khayyam and Nasir al-Din al-Tusi. Al-Tusi, in particular, recognized a flaw in Alhazen's argument and produced his own refined attempt. This chain of inquiry, stretching from Alhazen to al-Tusi, eventually reached European mathematicians like Girolamo Sacri in the 18th century. Sacri, who also used a similar quadrilateral, stands as a direct intellectual descendant in this long, arduous quest that ultimately culminated in the independent discovery of hyperbolic geometry by Lobachevsky and Bolyai. Alhazen's effort, while a failure in its stated goal, was a magnificent failure that fertilized the ground for one of mathematics' greatest revolutions. His mathematical curiosity extended with equal intensity into the domain of number theory, a field concerned with the properties of integers. Here, he confronted another ancient problem inherited from the Greeks, the nature of perfect numbers. A perfect number is a positive integer that is equal to the sum of its proper divisors, the divisors excluding the number itself. The first perfect number is 6. As its proper divisors are 1, 2, and 3, and 1 plus 2 plus 3 equals 6. The next is 28, whose divisors are 1, 2, 4, 7, and 14, which also sum to 28. Euclid, in his asterisk elements asterisk, had provided a powerful formula for generating these numbers. He proved that if a number of the form 2 to the power of p minus 1 is a prime number, a number now called a prime, then the product of this prime and 2 to the power of p minus 1 is an even perfect number. The unanswered question was a converse, are all even perfect numbers generated by Euclid's formula? Alhazen, in an untitled manuscript, was one of the first mathematicians to explicitly state that every even perfect number must be of the form described by Euclid. He provided an elaborate, though incomplete, argument for this claim. He was attempting to prove what is today known as the Euclid-Euler theorem, a cornerstone of elementary number theory, finally proven rigorously by Leonhard Euler in the 18th century. Alhazen's contribution demonstrates a profound intuition for the deep structure of numbers. He was seeking a complete classification, a way to show that Euclid's construction accounted for all possible instances of this unique numerical property. His work on this problem, along with his formula for the sum of the first 100 natural numbers, and his work on summing powers of integers, what is now known as Alhazen's formula for the sum of fourth powers, showcases a mind deeply engaged with the abstract beauty and order of the mathematical universe. This work on sums of powers was instrumental for the later development of integral calculus, providing a method for what is effectively the integration of the function x to the fourth power. This profound engagement with the abstract architecture of numbers provides the essential key to understanding the full scope of Ibn al-Haytham's intellectual project. His explorations into the properties of integers and the summation of series were the internal scaffolding for his grand ambition to describe the physical world with the unimpeachable certainty of a geometric proof. The rigor he applied to perfect numbers was the same rigor he demanded from his explanation of a rainbow. To comprehend Alhazen is to recognize that for him, mathematics and physics were completely intertwined expressions of a single, rational, and noble cosmos. His legacy, therefore, resides in the powerful methodology that unified his diverse discoveries, forging a new grammar for scientific inquiry. The ultimate testament to the synthesis is his masterwork, the asterisk Kitab al-Manazir asterisk, or asterisk Book of Optics asterisk. Within its 7 volumes, we witness the complete deployment of his intellectual arsenal. He begins with a problem inherited from antiquity, the nature of vision, but approaches it with a discipline that was entirely his own. He systematically dismantles the extramission theory of Euclid and Ptolemy, which proposed that the eye emits rays to perceive objects. He does this through a combination of anatomical evidence, physical experiment, psychological observation. He considered the anatomy of the eye, drawing on the medical knowledge of Galen to argue that its structure was suited for receiving light, a passive organ of sensation. He observed that looking at a bright light causes pain, and after images, phenomena inexplicable if the eye were an active agent. Most powerfully, he constructed physical proofs. His use of the asterisk al-Bayt al-Muleta 1E93 asterisk, the dark room, or camera obscura, was definitive. By demonstrating that light travels in straight lines from a source passes through a small aperture and forms an inverted image on the opposite surface. He provided a compelling physical analogy for the function of the eye. This was empirical science of the highest order. He isolated the phenomenon, controlled the variables, and produced a repeatable demonstration whose conclusion was inescapable. He then translated this physical observation into the language of geometry, using ray diagrams to model the path of light from each point on an object to the surface of the eye. This fusion of experiment and mathematical modeling established a template for physical science that would echo for a millennium. His work on catoptrics, the study of mirrors, and dioptrics, the study of lenses, followed the same exacting protocol, culminating in the formulation of what is now known as Alhazen's problem, a fiendishly difficult geometrical question about finding the point on a spherical mirror where light from a source will be reflected to an observer's eye. His solution, using conic sections, represented a tour de force of geometric reasoning applied to a real-world physical question. The transmission of this powerful new science into Europe is one of the pivotal chapters in intellectual history. Around the year 1200, the asterisk Tidat Almanazir asterisk was translated into Latin as asterisk or aspectibus asterisk, and its impact was both immediate and transformative. It became the foundational optical text for centuries, its authority rivaling that of Euclid. The English friar Roger Bacon, writing in the 13th century, was one of its most fervent disciples. Bacon's call for asterisk scientia experimentalis asterisk in experimental science in his asterisk opus magus asterisk was a direct echo of Alhazen's methodology. Bacon explicitly praised Alhazen above all other authorities on the subject of optics, recognizing that the man from Besser had provided something revolutionary, a way of knowing built upon tangible proof. Following Bacon, the Silesian scholar Whitelow produced his own monumental work, asterisk perspective or asterisk, around 1270. This text was, in essence, a vast and systematic amplification of Alhazen's asterisk or aspectibus asterisk, expanding its mathematical demonstrations and organizing its principles into a comprehensive textbook that would dominate European universities for 300 years. Through Whitelow, and also through the more concise summary by John Petcham, Alhazen's ideas on light, vision, and scientific method became standard curricular material, shaping the minds of generations of European thinkers. They learned about the camera obscura, the anatomy of the eye, the laws of reflection, and the principles of refraction through the lens of Alhazen's work. They absorbed his implicit lesson that a claim about nature requires more than philosophical coherence. It demands experimental validation and mathematical structure. This long intellectual apprenticeship culminates dramatically in the early 17th century with the work of Johannes Kepler. Kepler's quest to understand the structure of the cosmos led him to a critical astronomical problem, the precise path of light from the planets to an observer on Earth. To solve it, he needed a correct theory of vision. He turned to the established authority, which was a tradition of asterisk perspective or asterisk originating with Alhazen and synthesized by Whitelow. Kepler's 1614 masterpiece, a work that would revolutionize optics, bears a title that is a direct acknowledgement of the slimmage asterisk ad vitalium parallelumner quibus astronomiae pars optica tribiter asterisk, which translates to supplements to Whitelow, in which the optical part of astronomy is treated. Kepler saw himself as completing the project that Alhazen, via Whitelow, had begun. He adopted Alhazen's core principle that light radiates from every point of a luminous object and that the eye functions as a receptive instrument. He built upon Alhazen's work on refraction and the camera obscura to finally solve the puzzle of the retinal image, correctly proposing that the eye's lens focuses light to form a real, inverted image on the retina at the back of the eye. This was a final, crucial step in overturning the last remnants of ancient visual theory. It was a discovery made possible because Kepler was standing, as he well knew, on the foundations Alhazen had laid 6 centuries prior. The dialogue between them, conducted across ages and cultures through the medium of texts, represents the very essence of scientific progress. To measure the full stature of Ibn al-Haytham, we look to the principles that now feel self-evident, the conviction that scientific assertions demand empirical evidence, the requirement that physical theories possess mathematical elegance and predictive power, the understanding that science is a process of systematic doubt, rigorous testing, and the incremental building of knowledge upon proven foundations. These are the pillars of modern scientific enterprise. Alhazen of Basra, the brilliant, solitary scholar feigning madness in a Cairn library, gave these pillars their first clear and coherent articulation. He was a physicist, a mathematician, a psychologist, and an astronomer. Above all, he was the architect of a method that empowered all the scientific inquiry that would follow. His enduring legacy is the very expectation of proof, the intellectual framework that continues to guide our exploration of the universe from the quantum realm to the farthest reaches of the cosmos.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.